Cloud computing has pushed computation away from our own private servers and into virtual machines running on a data center. In the world of cloud computing, processing is centralized in these data centers, and our smartphone and laptop application performance suffers from having high latency between the client and the cloud server. As machine learning proliferates, the current model of cloud computing will become too slow. A small difference in the time it takes to refresh a machine learning model for a drone or a car could be the difference between life and death. Computation will move to the edge. The same drones and cars and IoT devices that need their models updated quickly will form a peer-to-peer network with which to distribute time-sensitive tasks. One bellwether for this real-time peer-to-peer network might be Uber's Ringpop, a fault-tolerant application layer sharding system. In such an edge computing model, as described by Peter Levine, a partner at Andreessen Horowitz, your device could federate a complex request out to nearby devices that have spare processing capacity. You could also pay for those compute cycles using Bitcoin and receive a response without any request being made to a centralized cloud server. The cloud servers would still be around, but they would be responsible for doing offline computation across large data sets. This prediction was described by Peter in his talk, The End of Cloud Computing, which I've linked to in the show notes. I found it to be a very interesting and thought-provoking topic, especially the thought experiment that provoked his idea for how to even come up with the insight of this edge computing model, which is the idea of subtracting something in order to figure out how computation will change. So in this episode, Peter discusses the pressures that are pushing us towards edge computing and away from the cloud. Dice helps you easily manage your tech career by offering a wide range of job opportunities and tools to help you advance your career. Visit Dice and support Software Engineering Daily at dice.com/sedaily and check out the new Dice Careers mobile app. This user-friendly app gives you access to new opportunities in new ways. Not only can you browse thousands of tech jobs, but you can now discover what your skills are worth with the Dice Careers Market Value Calculator. If you're wondering what's next, Dice's brand new career pathing tool helps you understand which roles you can transition to based on your job title, location, and skill set. Dice even identifies gaps in your experience and suggests the skills that you'll need to make a switch. Don't just look for a job. Manage your tech career with Dice. Visit the App Store and download the Dice Careers app on Android or iOS. To learn more and support Software Engineering Daily, go to dice.com/sedaily. Thanks to Dice for being a new sponsor of Software Engineering Daily. We really appreciate it. Peter Levine is a partner with Andreessen Horowitz. Peter, welcome to Software Engineering Daily.
Thank you. Good to be here.
You did this thought experiment where you decided to take the current model of cloud computing and think about what it would take for it to come to an end. And you say that if you want to predict the future of computing, you should subtract something from the world and imagine what could replace it. Why is this a useful thought experiment?
Well, nothing lasts forever. And, if back in the early 80s, one were to think about mini computers, like eventually that ended and PCs became the big thing. Or, 10, 15 years ago, Microsoft was like the dominant computing vendor on the planet. No one could ever imagine like Microsoft being nothing but bigger than they were then. And guess what? They're still big, but there are many other competitors that have come in and many other technologies that have come in. So I started to think like we are, as humans, we're very sequentially oriented. And so we have a particular topic and we say, okay, what's the, obvious sort of next thing that would happen after that? And our thoughts are always very sequential. Back to late 1800s time frame, if you asked a person, let's say you had horse-drawn carriages, if you asked the person what they'd want, they'd say they need a faster horse, right? Because that's the sequential thinking on that idea. Like, give me a faster horse and like, we'll go faster. But the technology that obviated the faster horse was actually the automobile. So in my view of the world, like, take away the horse, take away the carriage, and go figure out what fills that hole. And so in the modern day, I said, and it's always with things that are really popular, where you always think like, that will never end. Like, cloud computing will be here for the next billion years.
Yeah.
Well, it won't be. And so I said, like, take something really popular and take it away and go try to figure out what's going to take its place.
So you present the centralized model of computing in this talk that you gave, which is basically you've got a consumer device, whether it's a laptop or a phone, and that device requests information from a powerful server sitting in a data center. The data center is the point of centralization. What are the forces that are pushing towards a more decentralized model?
Well, one of the forces is the notion of real-time response is a forcing function. And so, while I don't want to always overload it, a self-driving car is a great example of processing requiring of movement to the edge. Because if I don't have real-time processing and real-time response, and I have to wait for the latency of some information to go back to the cloud, I'm going to go through a stop sign and kill 100 people before the cloud responds back to say, hey, there was a stop sign there. So I think the notion, for the first time, we are collecting real-world information, and we need to process that information very quickly in order to have a response. And so I think, to me, that's the fundamental sort of movement from a centralized model to this new edge model. It's purely about response time and the amount of information that we're collecting.
So the edge model that you describe is basically the cloud moves to self-driving cars, to drones, to IoT devices, and that is in some sense necessitated because we're going to have these devices and we need them to have faster response times. But it's also opportunistic because once you just start to have these devices around everywhere, that's a lot of compute power sitting around waiting for people to take advantage of it.
Sure. Yes. A self-driving car is a data center on wheels. A drone is a data center with wings or propellers. A boat, aircraft, whatever. These are all, they're all data centers.
So you're describing this world where there are trillions of devices. What are some of the ways that our current models of infrastructure and computing start to have fundamental breakages in that environment?
Well, network latency as an example. If a trillion devices are connected back, there's latency all over the stack. One is the network going from the edge device back to the data center. Then there's the processing at the data center. There's the storage at the data center. And there's the networking infrastructure at the data center that all completely gets overloaded when I have a trillion devices trying to connect to the data center. Like, it's just too many devices wanting this poor data center to have to process all this information. It's just not going to happen. So I think the current stack just is not capable of handling the amount of information that needs to be handled. And remember, when I think about this information, again, I'll go back to, we are collecting the world around us in terms of information. Trees and flowers and stop signs and light posts. And this is rich, deep, complex information. It's not a text string of 100 characters, right? If a trillion devices had a text string of 100 characters, yes, the cloud could support that. But these are gigabytes and gigabytes and gigabytes of information that needs to be processed at the endpoint. I couldn't imagine transferring that across the network, having it go into a data center where there's all this information that then needs to be processed and reported back on. So it's the nature of the information as well.
Couchbase is a NoSQL database that powers digital businesses. Developers around the world choose Couchbase for its advantages in data model flexibility, elastic scalability, performance, and 24/365 availability to build enterprise web, mobile, and IoT applications. The Couchbase platform includes Couchbase, Couchbase Lite, which is the first mobile NoSQL database, and Couchbase Sync Gateway. Couchbase is designed for global deployments, with configurable cross-data center replication to increase data locality and availability. Running Couchbase in containers on Docker, Kubernetes, Mesos, or Red Hat OpenShift is easy, and at developer.couchbase.com you can find tutorials on how to build out your Couchbase deployment. All Couchbase products are open source projects. Couchbase customers include industry leaders like AOL, Amadeus, AT&T, Cisco, Comcast, Concur, Disney, Dixons, eBay, General Electric, Marriott, Neiman Marcus, PayPal, Ryanair, Rakuten/Viber, Tesco, Verizon, Wells Fargo, as well as hundreds of other household names. Thanks to Couchbase for being a new sponsor of Software Engineering Daily. We really appreciate it. What about the storage model? Because if you start to distribute this data throughout this huge network of devices that's just floating around in space, how does the storage model have to change? Is it more like the data center is the disk and the devices that are driving around or flying around are the caches?
I would say yes to that. I believe that persistent data gets recorded back. So in the sense that disk drive, there won't be disk drives, but I'll call it non-volatile RAM or some persistent
Von
storage.
Neumannly.
Yeah, back in the data center, that will absolutely be the case, because then you have one authoritative view of the data, right? Now, the place where, so the notion of a cache is probably a little, in my mind, a little overloaded and simplistic, because in addition to capturing information and making real-time decisions, the information at the edge will need to be curated. And so when I collect gigabytes and gigabytes of real-world information, I don't need to store all of that, okay? So the edge becomes a curation device to maybe I sample that information or take the most important bits and pieces of that information to store back in the persistent data in the cloud. So it's much less than what I'm actually collecting. So in that sense, it's not a cache necessarily, but it's a curation machine at the edge. And then you have a cache that's propagating that information back to the cloud. That's how sort of I view it. And as I've said, and maybe we can certainly talk about this, I think machine learning is the ingredient that unlocks this new modality. And the learning is going to occur back in the cloud. So we need some information to go back to the centralized cloud such that the algorithms get smarter. And then those algorithms then get propagated back out to the edge to where we can do a better job curating that information. So there's sort of an iterative loop there just in terms of what the cloud's role is, how information is stored, and then what the edge role is, and it's working together. But storage, of course, is always a big deal, but that's how I would view it happening.
Sure, yeah. And so I'd love to talk about machine learning, but I first want to talk about something a little more far-flung, because this sounds like a world where Bitcoin really starts to matter, because if I'm wearing some kind of device or if I've got a car and I want that device to be able to perform an operation really quickly across a lot of data, then maybe I have to federate that request out to a bunch of nearby devices or something like that.
I love it, yeah.
So, I mean, does that sounds
love it.
Plausible to you? Absolutely.
I think the transaction engine in Bitcoin and the ledger and the notion of a distributed ledger, I've always thought would have applications beyond, let's say, just, moving money, right? And to me, it's a very interesting application. And I believe that there will be many new applications being written around this notion of a distributed compute set, right? It may be peer-to-peer, back to peer-to-peer. It may be this, Bitcoin ledger. It may be other things that will be innovated over the next N years here to support this distributed model of computing. So
and probably some full new set of algorithmic theories around actually the financial transactions paired with how are we valuing this little bit of compute that we're fettering out?
Absolutely. Yes, all of that will absolutely be part of what I'll call the innovation cycle moving to edge computing. Just like we saw, this happened in the past. 20 years ago, we were moving to a world of distributed computing. We had clients and servers, and clients were stateful machines that did a lot of work, and there were a tremendous number of innovations that occurred at that particular point in time in networking and in compute and moving information back and forth. Same with cloud computing. There were a number of innovations that occurred, virtual machines and microservices now, and all, back-end storage are all part of the cloud computing wave. And I think this new wave of edge computing is going to drive innovation in everything from infrastructure, transactions, and I even think programming languages will change as a result of the type of information that we need to process.
So one of the phenomenons that we've seen with the smartphone production ramping up is that the market has gotten a surplus of components that go into a smartphone. Many of these are the same components that can be used to build drones and cars and sensors. How are you seeing the capabilities and the economics of hardware components changing, and what are the bellwether signs of how close we are to this edge model?
Well, first of all, the mobile supply chain has influenced many of these, many of the cost reductions that we see even in cloud computing today, right? The mobile phone, there's no spinning disk on your mobile phone. Well, now there's hardly any spinning disks in the data center. So a lot of these technologies have come from mobile and have now been applied across the compute landscape. I think one of the most interesting on a go forward basis and a point of evidence on sort of hardware, the reduction and the commoditization, mobile phone commoditization, and how it relates to hardware in these devices is a LiDAR sensor in a self-driving car 5 years ago was like a $75,000 item for a car. And now, because sensors have gotten so inexpensive, it's like $500. And in 3 years from now, it might be 50 cents, right? And so I think that this, the mobile supply chain and the proliferation of mobile devices and the technology is a huge win and huge on-ramp to edge computing, because many of those components are very, very inexpensive now. And so all these new modalities can be created out of these literally mobile phone parts, including data centers, by the way.
Yeah, and then on the software side, Andreessen Horowitz has invested in the Berkeley big data analytics stack pretty aggressively, the Spark, Alluxio, Mesosphere, and this future seems like the future that you're describing seems like it suits the Berkeley stack pretty well, because it really puts distributed systems first. You've got Alluxio with the distribution of memory management. You've got Spark on the processing side. You've got Mesos that's like the God's eye view into managing these huge distributed architectures. When you look at the current open source landscape for managing these really big software systems, where are the gaps that you see? What are the opportunities and the problems that lie between the software space that we have now and the one that we might need in this edge computing world?
I think the Berkeley stack, it's a great analogy, and thankfully we saw that years ago already and made those investments, so I'm glad we made those. I think all of those projects and now companies solve today's issues and maybe problems that they're all more data center oriented than like full edge computing, because that's where the world is today, and that's great. Many of those technologies can lead to edge, but the notion of managing 1 trillion devices has all kinds of interesting ramifications in terms of what the next generation of, let's say, management software needs to look like, or the next generation of storage software that may need to distribute small fragments of data around a peer-to-peer network, right? And while Mesosphere, Alluxio, and Databricks are fantastic, great companies, I think we're going to see a next generation set of technologies that are managing very small bits of information or very small bits of services. I mean, maybe I'll call them very small bits of services. I mean, maybe I'll call them nanoservices. Like, we have microservices right now. And certainly Mesosphere and Alluxio are playing in, and Databricks are playing into that market. But I think there's probably an order of magnitude, more complexity that will need to be managed as the objects being managed become that much more prolific and smaller in nature, right? So, it's probably literally an order of magnitude, more number of devices, more number of processes, more number of storage elements will need to be managed. And I think that's going to be the opportunity for innovation in this area, will be in building those systems to manage that type of complexity.
You talk more about the peer-to-peer network and what the characteristics of that might look. Any predictions, or just too vague at this point?
My sense is that these edge devices will self-compose themselves and therefore create a collection of devices using some form of peer-to-peer. And I don't know if we call it peer-to-peer because that's already an old-fashioned term and didn't work very well in the past. But like this notion of these edge devices, I would say self-organizing themselves to provide compute power. Okay, so I can imagine whether it's automobiles or computers on light poles, like coordinating a compute, literally coordinating and self-aggregating into a data facility using themselves as the information or the constituency of that particular pool of compute. And I think that lends itself to peer-to-peer computing between those devices, networking between those devices, and storage, the storage communication between those devices. So all that has to be sort of figured out.
To understand how your application is performing, you need visibility into your database. Vivid Cortex provides database monitoring for MySQL, Postgres, Redis, MongoDB, and Amazon Aurora. Database uptime, efficiency, and performance can all be measured using Vivid Cortex. Don't let your database be a black box. Drill down into the metrics of your database with 1-second granularity. Database monitoring allows engineering teams to solve problems faster and ship better code. Vivid Cortex uses patented algorithms to analyze and surface relevant insights so users can be proactive and fix performance problems before customers are impacted. If you have a database that you would like to monitor more closely, check out vividcortex.com/sedaily to learn more. GitHub, DigitalOcean, and Yelp all use Vivid Cortex to understand database performance. At vividcortex.com/sedaily, you can learn more about how Vivid Cortex works. Thanks to Vivid Cortex for being a new sponsor of Software Engineering Daily, and check it out at vividcortex.com/sedaily. So you have described machine learning as being pretty crucial in this conversation. You say the data center basically becomes the place where a lot of the machine learning takes place, a lot of the large data sets sit. Maybe what are some of the other ways that the machine learning architecture drives this world and ends up changing the world of edge computing?
Machine learning is probably the only way, only is probably too strong a word. Machine learning is a mechanism for processing complex information, right? And so if we are collecting through sensor ubiquity at the edge, the world around us, machine learning and artificial intelligence is the way to make sense of all that information. So I don't think you can take a standard sort of program today, a non-machine learning algorithm, and apply it to this kind of information and get the richness out of it. I mean, we've seen now where, computer algorithms through machine learning are better than the human eye at identifying objects. Well, that object recognition happens through machine learning, and that's unlocked kind of this next generation of computing. And so as we collect all this information, I have to recognize objects and recognize certain types of data in this very complex, I'll call it, image of information. And it may not be a visual image, but image of data. Machine learning is our vehicle, no pun intended, but our vehicle for actually exposing the necessary elements out of that data. And so in my mind, it becomes a critical component and a critical enabler in this new world of edge computing. Now, those algorithms will work, the machine learning algorithms will work at the edge to process information very quickly and provide an answer, and then the learning will occur back in the cloud. So that's kind of how I see I'll call it the division of labor. But machine learning fundamentally operates on a premise where more data is better.
Yeah.
So the improvement in quote unquote intelligence occurs based on more data is better. So if I have 1 trillion devices and it's all feeding information back to this centralized sort of learning facility, think about how smart I can get by having all of these endpoints feeding me, again, curated information that makes the next turn on what I'm going to process that much better. And so I see that interlink between sort of number of devices, amount of data, and the functional, I'll call it expertise of both the edge and the cloud kind of working together.
So at this point, we've had a few years of machine learning really growing in popularity. There's so many people working on it. And I feel like we've probably started to figure out some of the canonical problems that we're going to be dealing with in machine learning as it becomes wider and wider spread. And one of the things perhaps is this batch versus streaming question where you have a machine learning model and it's perhaps tricky to update the model with a single example and you have to send it a batch of examples. And I just list that as an example of something that is maybe one of these canonical problems. So what are the other canonical issues of machine learning pipelines that we're seeing today and we're going to continue to see in the edge computing model?
In my mind, the amount of information and the real-time processing of this information is going to be a canonical issue until it's solved. I mean, everything is a canonical issue until somebody comes through with a breakthrough on it. I mean, 5 years ago, if you had said, hey, a machine is going to be better at identifying objects than the human eye, you'd say, well, we have a canonical problem there because it can't do it. Well, guess what? We can now do it. So in my mind, the notion, the problem tends to fill, the problem and the solution the white space tends to be filled through innovation. And if anyone out there has an answer to real-time processing of very complex information, we'd love to go look at that because that solves the canonical problem. And then there'll be the next canonical problem, whatever that might be. I mean, and so, thankfully, machine learning is at a point where I think it can be useful right now to do very beneficial data transformations in edge computing now to where we can start, and then we'll bump into always the canonical issue of where it can't work, and then we get better at it because a genius computer scientist somewhere goes and figures out the problem. And if any of you out there are the genius computer scientists, we'd love to talk with you because this is exactly where, that's the opportunity.
Sure. So you also hypothesize a shift in the role of a programmer, what a programmer looks like in this model. What are those changes that you envision?
I think that programming languages perhaps change from being logical, i.e., if this, then do that, which has been like the basis of compute languages, certainly since I've been programming. That's already a long time, or way before that, right? To a data-oriented programming model where we're actually looking at complex sets of data and applying sort of programmatic views on that data, not from an if-then standpoint, but from a object standpoint and from a let's look at that data standpoint as what information is important out of this set of data. And I think that programming languages may shift to be much more data oriented in this regard than, I'll say, programmatic as we have seen in the past. And so here we want everyone to be a programmer. In the not too distant future, perhaps everyone will be I don't want to overload the term data analyst, but a data hack. I don't know, create a name that sounds exciting, right? But it will probably be less about programming and more about the processing of data. And that will be where the change occurs, in terms of the expertise required in sort of the technical landscape. I mean, it's still software and it's still going to require deep technical skills, but I think some of that changes a little bit. And I think programming languages need to change to reflect this new world. So I'm excited about that. If somebody's got some great ideas there, we'd love to sort of think about that too.
So last question. Since this talk, I found it really interesting, and it seemed to spring from this thought experiment that you decided to run. Do you have any other unusual thought experiments that spur kind of creative thinking, or particularly in the realm of computing?
When I come up with it, I'll let you know. This to me is like the big one, we're going to erase cloud computing. That's pretty big. Let's hold on that one.
Well, I mean more abstract. The abstract idea. The abstract idea, like, you subtract something to like try to figure out something. That's kind of cool.
Like I said, I've when I come up with the next one, I'll let you know for sure. Like maybe it's the end of edge computing and back to centralization. Just inevitably that will happen. But anyway, cool. Yeah, I'll let you know when I think about it.
All right, Peter Levine, thanks for coming on Software Engineering Daily.
Yeah, thanks a lot.
Listeners have asked how they can support Software Engineering Daily. Please write us a review on iTunes or share your favorite episodes on Twitter and Facebook. Follow us on Twitter at software_daily or on our Facebook group called Software Engineering Daily. Please join our Slack channel and subscribe to our newsletter at softwareengineeringdaily.com. And you can always email me, jeff@softwareengineeringdaily.com, if you're a listener and you want to give your feedback or your ideas for shows or your criticism. I'd love to hear from you. And of course, if you're interested in sponsoring Software Engineering Daily, please reach out. You can email me, jeff@softwareengineeringdaily.com. And thanks again for listening to this show.